today is the topic is on the sequence design and artifacts and some of the nomenclature. So this section is supposed to be a little bit more like introductory, but mind you, because you already have found out that all those basic knowledge and points that you have learned so far, they are all connected. So today, even though it's more like an introductory on the sequence design, you'll find that actually most of the points that you have learned before is also mentioned, and you can just take it as like a review section. So I hope this can give you some interesting and direct visualization of how MRI sequence is actually done. Right. So the most relevant classes before is this the RF pulse, the concept of RF pulse, the gradient and the signal readout, and some of the simple MR sequence that are already been introduced before, like the gradient echo, spin echo, and the inversion recovery. And also, this is very important if you try to design a sequence. You have to understand the case-based concept, how the case-based is being collected and filled in different trajectories. And very important is the consistency within the case-base. So today we are going to take a look at major MR sequence components, how you do MR sequence design, and how to set up the imaging parameters, what consideration you need when you are doing that, and how it is actually done. There will be some tricks that we can use when tackling the sequence design and to tackle the artifact whenever it happens. And we also give some examples on the sequence and some of the nomenclatures that is involved. So, first of all, let's take a look at the MRI sequence 1, 2, 3. So it's literally 1, 2, 3. The essential component when you come to designing an MRI sequence, it's only three things. The first thing is the RF pulse. Second thing is the gradient, and the third thing is the ADC, the analog to digital converter, which is we usually call it a readout. Okay. So when we are designing the MR sequence, no matter how complicated the sequence is or whatever the sequence is used for, you only need these three components. So basically, it's very simple, right? So when you take any other components that you may come across is all peripheral. So MR scanner is a very complicated system. So we need other peripheral functions to help to facilitate the imaging process. So sometimes the peripheral would include like a patient positioning. So we need to precisely put the objects into the center of the ISO center of the magnetic field, and we also need the imaging processor to process the collected signals so that it can directly give us the image to look at, and also the RF coils to collect the data, right? So this is the sketch of the typical MRI scanner. So we can see that it's actually it's comprised of many different components. So basically, the hardwares from the gradients, the magnetic fields, and the main computers that perform the controls. Okay. So from another angle, when we view the MR sequence, there's also three main functionalities that MR sequence does. So the first thing is signal excitation. So for any sequence, you at least have something that can excite the signal. so that you can have something to detect. Otherwise, you can just detect noise. And there is also a signal preparation or manipulation or modulation. So that this signal modulation or manipulation give you different image contrast. And also the signal acquisition. The signal acquisition, the way the signal acquisition, as we mentioned before, it will also affect how you feel the K-space, also affect the image contrast, and also the signal and noise, right? Signal to noise ratio. So it's very important. So you can all view the MRI sequence from a very simple point of view. So it's just like these three main functionalities. But when we are talking about them, so after all, then what is MR sequence? So if we look at these components, you can say that MR sequence is a time series of play out of all these components. Or we can say an MR sequence is a series of radio frequency pulse, gradient pulse, and signal readout to perform all these functionalities. So here are some examples. So this one, as we have seen many times before, is a simple 3D gradient echo sequence. This one here, we also have shown before, it's a gradient echo EPI. This one is a single spin echo EPI. And this one is a single spin echo EPI. We can see that it's 2D because it only has phase encoding along one phase encoding direction. And this is a fast spin echo that collects multiple spin echoes with a single excitation. So these are the the most routinely used sequences that we can come across. Just as we said before, we can all break them down into three simple components. So take example for take the gradient echo EPI, for example. So we can have one RF pulse here, many different types of gradients, and only have the readout. It's not shown here. It only shows the echo, but we have the readout to collect all these different a series of gradient echoes. So we can break down into in that way, or we can break it down into the functionality category. So this one here is the signal excitation. It has this. This one is a complicated RF pulse that can give you a spatial, both selective excitation on the spatial and the spectral domain. So this is a spatial spectral excitation RF pulse. So this one is has the functionality for excitation. This one, they have the functionality of signal phase encoding and frequency encoding. So we can consider them as the signal propagation. And also we have the readout gradient here to read out all these echoes. So so this is some simple examples. I'm sorry?
What is the significance of this special RF pulse?
Okay, so this one is actually it's called a spatial selective gradient. So usually, RF pulse. So if we use single sync pulse, right, by itself, it's a spectral selective, right? It has a certain frequency, and when combined with the gradient, it now becomes a spatial selective. So when we do this, it is still actually a relatively wide band frequency. So it means its bandwidth is actually quite wide. So it will excite for example, both the water and fat. But for this one, it's also more like spectral selective. So it not only has this spatial selective functionality, it also is more spectral selective. So it can only excite the water signal without exciting the fat signal. So this is sometimes even more effective than first applying fat saturation before the excitation. Right. Okay, so first let's take how an MRI scanner generate the RF pulse. So this is the diagram. It's actually from a patent file a long time ago. So this is a diagram of the MRI system. So to generate an RF pulse, we first will have this MRI sequence controller. So after we have programmed the MRI sequence, we insert this sequence into the system. So the system would, so this controller will interpret the program we write, so that break it down into the electronic signals with a specific timings. So this controller system would then forward the timing and the timing and the strength of the gradient pulse to this MRI sequence controller. So this MRI sequence controller would also then forward it to the to this. Okay. Oh, sorry, it's the RF pulse. So this controller now forwards the parameters of the RF pulse to the RF transmitter amplifier. So this one is now the analog, but nowadays I think they all are the digital amplifiers now. So using the RF transmitter amplifier, it will output the RF pulse, and then the RF coil, when the RF coil receives the current generated from the amplifier, it will give us, it will give out a series of RF pulse with the timestamp and strength as indicated. So the requirement for generating a good RF pulse is usually that it will have a spatially homogeneous electromagnetic field. So usually we denote the RF pulse field as the B1. So the ideal is that we can generate a very spatially homogeneous RF field so that it can excite all the spins with the same flip angle, same frequency response throughout the whole object. So usually that's the idea. So using the RF pulse to create transverse magnetization, as we have seen before, it follows the basic block equation showing like this. So it means that any magnetization actually will precess around any external magnetic fields. So by generating a B1 field, the RF field, the magnetization will also precess around this B1 field, so that it will have a tipping effect of this to this magnetization. So as we have shown before, if we use a laboratory frame, we will be observing a very complicated precession of the magnetization from the equilibrium when it sees RF pulse. So it will have the tip down effect from the longitudinal to the transverse plane. But in the meantime, because it has a component that is now perpendicular to the external field, so now for that component, it will also have this precession motion. So this is a very complicated scenario. So if we do this in a rotating frame, so that the reference frame is also rotating at the same frequency as the Lama frequency, so that we can simply observe the tipping effect of the B1 field. So we can see the magnetization is now simply being tipped from the longitudinal axis to the transverse plane. So this RF pulse usually when when we apply the RF pulse, it is also using the frequency that is the same as the Lamarck frequency we are interested. So the RF pulse properties, okay. So first thing is we can have an on-resonant RF pulse, or we have an off-resonance RF pulse. The difference is between is that whether the frequency of the RF pulse is the same as the Lamarck frequency of the spin that we're interested. So if the frequency of the RF pulse is the same, then we call it as the on-resonant case. And if the RF pulse frequency is different from the Lamarck frequency, then we call it an off-resonant case. So most of the time is we can see it later. So also there is another the flip angle. The flip angle will indicate the tipping effect of the RF pulse. So it means how much signal we can obtain when we apply an RF pulse. And there is another frequency response. So when we play our RF pulse, we have to play it out in the temporal domain, right? In the time domain, because we are living in time. So, but its frequency response, we can view it simply using the Fourier transform of this RF pulse of this P1 field. So if, for example, if we have applied a sync pulse in time domain, then we can obtain a rectangular response of the frequency in the frequency domain. So that means the spins that has the frequency between this within this bandwidth range, they all have the same. They have been experience the same excitation process. Or we can say the flip angle for the spins within this band frequency range are the same. So if we apply the Gaussian RF pulse, because the Fourier transform of a Gaussian function is also Gaussian, so we can see that the frequency response is also a Gaussian. So at this point, only a very small fraction of the spins can considered to be strictly on-resonant, while other spins, they are kind of more or less off-resonant. So usually we would use the concept of bandwidth. So when we use a bandwidth, we consider that all the spins that are within this bandwidth would consider to be on-resonant. So for this sync pulse scenario, we can consider all the spins that fall within this frequency response profile, they are on-resonant. But for the Gaussian case, we can define the bandwidth to be the half-width full maximum of this frequency profile, so that any spins that are within this frequency range are considered on-resonant, even though in fact they do not strictly have the same signal intensity, or they do not strictly experience the same flip angle effect. Okay, so there are many types of RF pulse. So RF pulse design is a very important and a very large subfield of MRI. So I'm only showing some of its, look at the RF pulse from different point of view. So if we look at them from the point of view from the functionality, we can consider them as, for example, the excitation RF pulse. So usually this excitation pulse is needed for every sequence, and usually is between 0 and pi over 2 flip angle. And also there is refocusing RF pulse. So usually we can see them in the spin echo sequence. So it's usually between half pi to pi, so 90 degree to 180 degree, or sometimes it can go over a little bit, go over to over the 180 degree. So another type of RF pulse is the inversion recovery pulse. It is used for the inversion recovery, so it can give you heavily T1 weighted images. It can also give you some tissue numbing if we carefully choose the correct T1. And usually the inversion recovery pulse is strictly pi, 180 degrees. So here are some of the principles of those RF pulse that you have already seen before. Okay, so if we look at the RF pulse from its temporal shape, so, which is the B1 field it generates, so we can divide them into different types too. So we can see the most widely used is the sync pulse, because it can generate a rectangular shape of the frequency response. So that means the frequency response it generates is relatively homogeneous. So it's widely used for spatially selective imaging, like the 2D imaging or even 3D imaging. There is this rectangular RF pulse. So rectangular RF pulse, its frequency response profile is the sync function. So usually we use the rectangular pulse as a non-selective excitation, or for the inversion recovery, because it can give you a very fast, very short RF duration, and it can give you very wide bandwidth. So for the Gaussian pulse, it is usually used for saturation. So for example, for the flex saturation that we usually use, it's given in the Gaussian form. And also, if you for the magnetic transfer contrast RF pulse, it is also in Gaussian pulse. And there are also some very strange shape, different shape. So like the Verse pulse, it is a very well rate selective excitation. So it will have a smaller amplitude at the center of the RF pulse to reduce the SAR level, which is the RF power deposition into the human body. And also there is composite pulses like the Shin and the Hu pulses. It can give you some minimal phase development for the excited signal. So this is from the point of view of the temporal shape of the B1 field. So if we look at selectivity of the RF pulse, it can be divided into the selective or the non-selective types. So for the selective pulse, we can also usually call them soft pulse, because it can give you a relatively narrow bandwidth and give you a very well-defined frequency response. So usually it's like using the sync pulse. Usually the sync pulse is implemented with a relatively long duration. So it's like 2.56 milliseconds to 5.12 milliseconds. So if we have a 5.12 millisecond long sync pulse, and it has a 4-0 crossing, we approximately will have the bandwidth of 780 Hertz. So this is actually a relatively small bandwidth when we are talking about the excitation pulse. And for the non-selective, we usually call it a hard pulse. So the hard pulse is usually implemented with very, very short duration, and to give very broad bandwidth. So when you give a hard pulse, it will excite almost every spin in the whole object similarly. So it's usually like given in as a rectangular pulse. And for example, you can apply this hard pulse with a duration as short as 50 microseconds. So it will give you a very wide bandwidth. So for this kind of bandwidth, that is our 10 kHz, it will basically cover all the possible frequency components that an object inside the scanner, inside the magnet can have. So basically, it will excite everything.
So these examples are for a specific V0 value, or?
No, it's everything. It's general. Yeah, it doesn't have to be along under a specific field strength. Okay, so we can also define an RF pulse in terms of its purpose. So, for example, we can call an RF pulse as a selective excitation or saturation pulse. Okay, we have this magnetic transfer contrast. It can be used to reduce the signal of a certain tissues via its off-resonance effect. We have this tune pulse. It gives you a spatially variable, it purposely gives you a spatially varied flip angle so that we can use it for MR angiography to reduce the blood saturations as it flows into the imaging slabs. So we'll talk about this in chapter 23. And also as the spatial spectral selective RF pulse we just mentioned, it can achieve both the selectivity in terms of the spatial and spectral domains. And there is also there's a spin lock pulse. It can give you another type of new relaxation parameters. It's called a T1 row, so it is a little bit different from T1. And there is also more complicated adiabatic pulses. The adiabatic pulse can achieve a uniform response even if the B1 field itself is not uniform. So these are the categorizing the RF pulse according to its purpose. So when we are designing the yes.
What do you mean by spin lock?
Well, spin lock is it's a little bit off the topic, and I need to spend a little bit more time to explain that. So we can do this after class.
Guessing, are we exciting different spins with different?
No, it's still the same. Actually, we are now when we are talking about T1, we have a very strong B0, right? So that the signal along this B0 is recovering using with the T1 constant, right? So now we applied a very strong B1. So now this strong B1 field itself forms a new strong field along which the signal can also recover. So now this B1 field, if we look at the rotating frame, this B1 field is the new B0 for the signal recovery. So that when the signal recovered along this B1 field, it is we then call this recovery speed as using the T1 row instead of the T1. So usually the T1 row sequence is a very SAR intensive sequence. So when we designing the RF pulse, we need to have several considerations. So first thing is the block equations works fine for the small flip angle approximations. But if the flip angle goes higher, then the result that is calculated from the block equation would become the error would become stronger. So we will need to use more advanced designing tools to design a large flip angle. So that's why we are seeing all those different types of RF pulse, like the adiabatic or Shin-and-Hu SLR RF pulse. So those are mainly developed to address this kind of problem. So we also need to consider the SAR, the specific absorption rate of the RF pulse, the position into the human body. So when we are going using a higher flip angle, or we are going to the higher fields, this SAR issue would become more and more intensive. So, for example, if we are scanning at a very high flip angle at 3 Tesla, sometimes you will feel the whole body will become very hot. So you'll be sweating heavily inside the scanner. And if there is no safety measures, usually the modern scanners, they have this safety measures. So it first will detect and estimate how much RF pulse would be deposited in. So if it's if it has exceeded the limit, it will advise you to stop. Actually, it will force you to stop. But if there is no such limits, there can be a possible burning injuries in the skins. So so when we are screening for a subject to see whether he is suitable to go into the scanner for an MRI scan, usually we have one option to see if they have this tattoo in their skins. So that's why, because the tattoo, they might contain some of the metals, they can actually increase the local SAR, so that it will increase the risk of being burned inside the scanner. Okay, so we will also need to consider a B1 field in uniformity. So we mentioned before, when we apply our pulse, we want it to have a homogeneous field strength all over the whole subject. But due to the dielectric effect, which will be worth and higher fields, the B1 field itself will not be very homogeneous. We can see this effect even starting at 3T. So we will see some example of this dielectric effect in later parts. And also we need to understand the frequency response profile to choose the correct type of RF pulse that meets our needs. And also we need to consider what kind of application we are using. So if we are trying to do a 2D or 3D, and we need to understand the contrast mechanism and also the safety and selectivity of the RF pulse itself, whether it's, it will give us the results and image contrast that we desire. Okay, so the next part is the magnetic gradient. Right, so we generally just call them a gradient. So the definition of a gradient is the spatially varying magnetic field, and we denote it as G. So the G itself is actually just the slope, the slew rate of this the magnetic field change that we deliberately applied. So that when we apply a gradient, magnetic gradient, we can observe a frequency change as a function of the locations. So during for the sequence design, we would denote a gradient with a slope rate of g as just as like a rectangular. So this is what it is shown in the sequence diagram. But actually, in the space, in the actual space, this is the gradient looks like. What the gradient looks like. So it's very similar for generating the gradient pulse to the RF pulse. So when we have designed our sequence, we have the timing and the duration and the strength of the gradient. We all input them into the sequence, into the MRI scanner. The MRI scanner sequence controller will pick out those informations and forward it to the gradient coils, the gradient amplifiers, and the gradient amplifier would then output required current to the gradient coils, to the 3 different sets of gradient coils to generate different gradients along the x and y and z directions. So the gradient pulse can actually be have an arbitrary shape. So and at slew rate, it means how fast it can be switched on and switched off, and the maximum intensity, maximum value is limited by the hardware. So usually when we denote an gradient pulse, this is more like a symbolic denotation. But practically, we have to allow it a certain period of time for it to switch on to reach its desired value. So when we are doing this, so this is the spatial distribution of the actual magnetic field, and this is the symbol of the gradient. So let's see how this strength of the gradient at different temporal points will correlate to this actual field distribution. So when there is 0, this is 0. There is no single distribution. When it goes up, the slew rate of this field variation goes up, and when it ramps down, the slew rate ramps down. So basically, this here is actually showing the slew rate of the actual field distribution. Okay, so let's take a look at this one. This circular gradient. It goes up, still going up, and it reaches the highest, strongest slew rate at the peak, and then it goes down.
Is it an actual example or just for demonstration?
Well, it is an actual example, but it is through simulation.
Oh, I mean,
Yeah.
Can we perform this on a real hardware?
Well, this is actually what it is done on hardware. So if you, for this part, if you have a series of sensors that you can place inside the magnetic field, you can actually detect the same distribution.
No, I'm talking about the shape of the gradient. So at the point 50 over there, it seems that we have a sharp rise, okay?
Which one?
The right.
50, yeah.
Yeah, okay. So we have a sharp rise, right?
Yeah, a sharp rise. So yeah, so for practically, it may have a more smooth transition at this part.
So I was thinking if we can really make this sharp rise, so why we have to do the
Okay. Yeah, this is. Yeah. Well, if you really want to be more specific, this is still also an ideal representation of what actually being done. So on the hardware, probably it will have a slightly smooth transition at this at this turning point. But and also we can see that for the positive part of the gradient and for the negative part of the gradient, would be corresponding to a different sign of the slew rate, the slope. So that means no matter what is the gradient shape is, when we do the design, we need to bear in mind that the actual field variation should be spatially linear at any time. Okay, so the gradient pulse, it has several properties. The first one is its directionality. So when we say a gradient, we need to specify its directions, whether it's along the x-axis, along the y-axis, or any arbitrary directions along the space. So we need to address this, and it would, if a gradient pulse is applied by itself, it will only affect the transverse magnetization only. It does not affect the magnetization that is along the z-axis. And but when it is used, when a gradient pulse is used with the RF pulse, in principle it can affect the magnetization in any state, even including those along the z-axis. So that's why you can do the excitation of it. So, right. Okay, so there is also a very important property of the gradient pulse is that it is linearly addable, that can be linearly added together with two different gradients, so to save time. But premises is that there is no radio frequencies or readouts between these two different gradient lobes. So, for example, if you plan to apply two gradients, consecutively, you can combine them together, partly combine them together, or you can fully combine them together. So the effect will be the same. And on the other hand, if you apply a gradient along z-axis, another gradient along y, and another gradient along x, as long as there is no RF pulse or readout between them, you can apply them at the same time. So it will give you the same results. And but if you have an RF pulse between these two, then you cannot combine them because the status of the magnetization is now changed by the RF pulse. So this can be used significantly improve the compactness of the sequence designs to make it save time or make it a faster scan, or sometimes you can push the limit to get you for example, a shorter TE or shorter TR, right? Okay, so if we divide the gradients according to their gradient lobes, usually we have this trapezoidal gradient lobe that is most commonly used. They're used for readout, slide selection, and phase encoding. Most of the time, what we are seeing, the gradients pulse we use are in trapezoid. And also we have this spiral gradient pulse. Usually it can give you this spiral readout. So usually it's used for the readout to give you a very fast acquisition of the whole K space. And there is also a triangle, or what we call blitz, which is used in EPI phase encoding. So, well, triangle is basically a simplified version of the trapezoid, right? And also there may be some special gradients that have a specific shape that is, combined with the use of RF pulse, like this Wurst pulse. When we modify the amplitude of the RF pulse at the center part, we also modify the gradient so that the selectivity of that of this part will remain the same as if there is no change. So it will still give you a very very good rectangular frequency profile. And also, if we divide the gradients according to their functionality, we can divide them like the readout gradient. We have seen the phase encoding gradient and the slide selection gradient. For the readout, we have this pre-phase gradient, so that we can move the pointer of the K-space to one end, and then we start collecting the lines. We have this D-phase gradient, so that we can spoil the residual transverse magnetizations for the steady state incoherent signal. We have this rephase gradient for the slide selection, so that the signal does not disperse. And we also have this spoiler gradient, cross-share gradient, and also the field compensation gradient. As we mentioned before, there is this C shimming technique that we use this field compensation gradients. And there are some of the sequences actually feature in the gradients that they use. So, for example, if we want to do a flow compensation, so we know that the moving spins, they would have a phase dispersion, right? So if we want to remove this phase dispersion caused by the motion or the flowing blood, there is this flow compensation gradients that we can use. So, and also if we want to detect how fast the flow is flowing, we want to detect the velocity of the blood flow, we can have this flow encoding gradients to give us this information. And also, if we want to remove the blood signal, we have this flow dephasing gradients that we can totally do remove the blood flow to give us the dark blood images. So we will discuss this in chapter 23. And also, for the diffusion weighted imagings, we would use a very strong and long gradients to enhance the diffusion effect, and we will call those diffusion gradients. So when designing the gradients, we need to have some of these considerations. So first thing is that we need to understand the maximum slew rate and the maximum value of the gradient that we can use given the current scanner. So when we are writing the sequence, we need to set the timing of the sequence so that the slew rate or the gradient amplitudes will not exceed the limit. And if sometimes when we use a very fastly switch gradients or very strong gradients, it can lead to some eddy currents inside the human body. So this eddy currents will actually lead to the nerve stimulation, making your muscles twitch. And also a very strong fast on and off gradient would lead to the physical vibration of the coils itself. And also it will lead to a very strong acoustic noise. So when you go into this for an MRI scan, you always need to plug in an earplug to reduce those noise. And also we need to consider the possible eddy currents effect that can pose on the image quality and the image distortions if the gradient, if we are pushing the limit of the gradient, it may lead to the linearity of the gradient to decay. So when we want a linear gradient, that is, the gradient itself is supposed to be linear throughout the space, but if we are pushing the limit of the gradients, sometimes it may lead to a nonlinearity. So that means that will also lead to the image distortion. So we saw this before when we are using the different strength of the gradient. If you scale the sequence differently, and also there is a spatially limited linearity of the gradient. So sometimes this would lead to a so-called third arm artifact. So when we say that a gradient is linear, we usually is referring to the linearity within a certain spatial range. So usually we define that as the FOV, right? The field of view. So as long as this field of view, the gradient between this field of view is linear, we can get a very good representative of the object, and there's a minimum distortion. But we will know that this linearity cannot go on, with unlimited distance. When the distance is, farther away from the center of the magnet, this gradient strength will fall off, and it may go back to zero. So if there is an object outside of the field of view, but it sees the same frequency, because this gradient, the gradient is now falling off at the edge. So now, and if you are using RF pulse, right, that also excites the whole signals, every signals here. So that means in the reconstructed image, the objects outside the field of view will also be considered to have the same location as the original object, so that they will overlap. So here is one example that I collected a while ago. We are imaging the brain here, but and I use a non-selective RF pulse. So for non-selective RF pulse, it has very wide bandwidth, right? So it excites everything, including those within our FOV and with those outside FOV. So even I was imaging the brain, I also excited the signal in the shoulder. And for that shoulder, for the signal excited at the shoulder, and it sees this the same frequency due to this decay of the gradient. So we can see that the shoulder now is overlapping with the brain. So we also need to decide which kind of gradients we need according to our image contrast, and sometimes we also need to consider the efficiency when we are designing the sequence. So if we take this, for example, excuse me. So if we use a higher gradient, we can have a shorter readout, and then we can have a smaller distortion effect from the background gradient, as we discussed in last section. But it will lead to a reduced SNR, right? Because we now require a higher bandwidth to collect the data. So it would also determine, depend on, the image contrast and specific purpose that we want to do. Okay, so for the slide select gradient, as we have seen this before, so this is kind of like a review here. So for RF pulse here, if the RF pulse is applied by itself alone, it has center frequency, it has bandwidth. So it's basically a spectrally selective. It gives you some spectral selectivity. So to convert it into the spatial selectivity, we will use combine it with a gradient. So according to here, RF pulse with different central frequency would excite a slice at different locations, and the RF pulse with different bandwidth will excite slice with different thickness. So usually this slice select gradient is used for the excitation or for the refocusing RF pulse in spin echo, or the inversion recovery if we want to do the selective inversion recovery. So we need to, so when designing the slice select gradient, we must make sure that the zeroth moment of the SS slice selection part must be 0 before the ADC turns on. So that means this rephase gradient is used to reduce rephase the dephasing effect from half or from the latter part of this slice select gradient, so that there is no dephasing effect from the slice selection gradient. So for the phase encoding gradient, in the sequence diagram, the phase encoding gradient, they are represented as the phase encoding table in the sequence diagram. So there may be a different phase encoding reordering schemes. For example, like the ascending or descending acquisition of the K-space lines or the center out. Sometimes we can see them also showing with an error in this phase encoding table. So the phase encoding itself, usually it's not, the major consideration for the phase encoding is to do the reordering, how to do the reordering according to your specific requirement on the image contrast, right? If you whether you want to collect a T2 star weighted or a T1 weighted, so that means you'll be using a different TE. So when that happens, you may need to consider a specific phase encoding reordering schemes. But usually, on the other hand, if we are doing a very large, a very high resolution imaging, that means we will need a very large number of phase encoding. So that means the phase encoding gradient needed for the collecting the outer part of the K-space will actually come in very large. So when that happens, it may affect the minimum TE that is available for the gradient for the sequence. So sometimes the minimum TE is what needs to be taken into consideration. And then it's the readout gradient. So for the readout gradient, it is combined with the ADC, the analog to digital converter, to collect those frequency encoded signal here. So the echoes that take place when the zeroth moment becomes 0 again. So if there is no background gradient, the echo will take place exactly at the center of the readout, as shown in here. But if there is background gradient, as we've seen before, then this zeroth moment would take place differently, in other place other than the center of the readout gradient. So that will effectively cause echo shift. So the sampling rate of this readout, if we know the readout bandwidth, so the sampling rate, the delta t between the two sampling points along the readout is actually the 1 over the bandwidth. So it's very simple. So the total time of the readout or the ADC sampling duration is the delta t multiplied by how many sample times you have, right? So it's basically just n delta t. So equivalently, if we know the bandwidth, it's n over over the bandwidth. So that means the total readout length is represented like this. So this is a very important equation, because sometimes the duration of the total readout would affect the TE we can have, would affect the minimum TR that we can have. And for it affects the minimum TR, and if we are collecting a fast, a short TE imaging that to acquire a steady state signal, a different TR would lead to a different signal due to the different T1 weightings. Okay, so for those who have done some MRI scans before, you know that the MRI scanner is very loud. So any of you have heard of those noise before? No? You? No. Okay. So here is some of the examples of those actual MRI sound that were recorded. So for example, for the 3D gradient echo here. So you're hearing that actually it's not a very high pitch, because the TR is roughly 30 milliseconds here. So the TR is roughly 30 milliseconds. That means this the frequency that you hear that is like 1 over 30 milliseconds. So it's not a very high pitch sound, and it goes on basically throughout the whole scan like this. So I'll just stop it.
What is the sound in between?
Sound in between what?
Yeah, the continuation of the sound is like frequency encoding, right?
Yeah, it seems that it goes up and down.
Yes, you have those up and down is the phase encoding gradients. Yeah. So the normal is the readout gradient, and if you hear it, from a longer, a wider span of time, you can hear the up and down of the phase encoding gradients. Yeah. And then here, the next one is the gradient echo EPI. So for the gradient echo EPI, we have a very fast switch on and off of the readout gradient. So that means this it will create a very high pitched sound. And on the other hand, for the TR level, so on the TR level, you will have this repetition of the TR. Usually is like 2 seconds or 1 second. So that would lead to another frequency, the sound, the repetition of the sound in a 1 or 2 seconds interval. So you will be hearing a high-pitched sound with 1 or 2 seconds interval here. So let's hear all this. Okay, so yeah, it's because we are collecting multiple slices during the TR. So it's actually, for example, it's roughly like 100 milliseconds between the one excitation to another excitation. So when you hear da 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 da, it's actually the sound. This interval is the interval between the different excitations, but then you can hear that the sound is very high pitch, right? So that high pitch part is caused by this readout. Okay, so that's the gradient echo EPI, and the next one is the fast spin echo. So for fast spin echo is a more slower sequence than the gradient echo EPI, although it is itself is still a multi-echo sequence. So for this one, the TR is even longer, and the readout, the interval between the echoes is much longer than this one. So you'll be hearing a lower pitch of the sound. So that is not as high pitch as in EPI. And you see here that each interval is the interval between the each excitations. So, all right. Okay, so the next one are some MRI music. Actually, people program the sequence to give you some songs. It's actually a competition that was held by the ISMRM, the International Society of Magnetic Resonance in Medicine. I don't know, it's a while ago, so people has come up with all these interesting musics. Yeah, actually, as long as your slew rate and the maximum gradient does not exceed the limits, the amplifier will handle it well. Yeah, and as I'll say that demand of the song we heard on the gradient system is not very strong. So it comes faster and faster. Huh? I didn't know. So in this case, we are still doing well with gradient coil here. And this one is my favorite.
He has recently patented a new technology named silence or something. That you barely can hear the gradient emotion. So
right. The silence sequence. The silence sequence is basically it's like a UTE sequence they call, right? Ultra short TE sequence. They use if I remember correctly, they use a constantly on readout gradient. So you read out, always reading out, and use a very small flip angle and something like that. So basically, it's because you have the radar gradient always on, there's no change of the gradient, so there is no sound. So I may be wrong, but that's my impression.
Can you tell us a little bit why these sounds are created?
Okay, why this sound? So when you have, when there is a magnetic field, right, and you have a wire going through it, and you have a current going through it, what does it do? It feels the Lorentz force, right? So if Lorentz force, so if this current is alternating, then this force would also be alternating. So that means there is a physical vibration in that wire. So it's the same thing here because the gradient coil, they are wires, right? The RF coils, they are wires. So when there is a gradient changes, so that means that to create a gradient, actually we need to give the gradient coils different levels of current, those alternating currents, right? So when this gradient coil is now like that wire in the magnet. Yeah, also it is also seeing the magnetic field, so it will also be vibrating. So that's the vibration of the coils.
So that physical vibration inside the magnet you feel, during like special sequences, like such as DTI is.
Mm-hmm. Yes, it is the same. Yeah, because for those you can hear, those acoustic noise you can hear are those high frequency vibrations, and for those you can feel in the whole magnet is shaking. It's relatively low frequency. Yeah, so usually you can feel that with the diffusion weighted imaging. It's because it uses a very strong and very long gradient. So the switching is not very fast, but when it switch, it will create a very strong force. So when it switch on, if it moves, and then it waits a little bit, and then it switch off, and then it will move again, right? So this duration makes it not too not very high frequency. So you can feel it. But also, in principle, you can also hear it. Okay, so here's some practical consideration of MR sequence programming. So before you do the work down, if you're interested to do the MR sequence programming, you need to know the exact goal of what you are doing, what you want to achieve. You want to achieve a steady state. You want to achieve T2 star imaging. You want to use a Cartesian, acquisition, or you want to use a radial acquisition. You must know exactly every goal you want to achieve, and also you need to know the major restriction and potential problems that are associated with the current method. And then when you have an idea a clear idea of what you need to do, you need to first draft up the sequence diagram first to make sure that you have a blueprint that you can work on. And during the program, and of course you have to go through thousands of codes, and but the most important thing you have to do bear in mind is the timing of the sequence. So the timing means the timing of those three components: the RF pulse, the gradients, and the ABC. So the timing is very important. I'm not sure about other scanners, but on Siemens scanner, the minimum timing unit is 10 microseconds. So you will have to be specific of the each component, the starting time, the duration. You have to be as precise as 10 microseconds. And you also need to consider the consistency and interaction between different parameters. Just as we mentioned before, if you change the bandwidth of the readout, you will also be changing the duration of the readout, so which will in turn affect the minimum TE and minimum TR that is available. So you also need to take into consideration of those factors. And also there are usually simulation tools that you can use to do the simulation and check on everything to make sure that everything works as expected. And of course, the most actually programming may not be the most difficult part and time-consuming part. Debugging and optimization would be the most time-consuming and demanding part of the MR sequence programming. So usually you need to do the testing, multiple testing and retest, and use the deduction, the method of deduction, to find out the cause of different problems. Because sometimes when the sequence is not ready, you will it's very likely that you will see either the sequence not working, stop halfway, or give you an image with artifacts. So you will try to use all kinds of methods to try to determine the cause of those problems. And also after the sequence is running smoothly, then you can further optimize the sequence design and imaging parameters and see if there is any room for optimizations. So when we are doing imaging parameters optimizations, usually we need to understand how all these parameters are connected to each other. So here is a plot, a connection map that I made based on my own experience on Siemens scanners. So usually when we are working on the Siemens scanner, we can input certain parameters, explicitly input certain parameters, like the FOV, field of view here, like the number of sampling points, and like the bandwidth here, like the bandwidth, the readout bandwidth, and TE or TR. And there are some implicit parameters that we do not need to input, but they will also vary or change according to our inputs. For example, we don't need to specify the gradient strength of the readout gradient, or we don't need to specify the duration of it, because it will be automatically determined once it has the FOV, the number of sampling points, and the bandwidth. So yeah, and we also when we are doing the optimization of parameters, we usually need to bear in mind the SNR dependence on different parameters. So yeah, so this will be useful. So for the section on the first day, we will further discuss on this map. Here. Okay, so here's some sequence examples here. So this is the 3D gradient echo we have seen multiple times. But if we are practically doing a sequence design, so we can see that there is something not practically right. So can anyone tell me? Readout gradient shifted? No, it's not.
Is it the exact rectangular?
Yes, that's right. So this can be a very a good conceptual diagram, but practically when we are doing the sequence design, we need to take into because the slew rate cannot be infinitely fast. So we will need to specify the slew rate it will give you a time for this ran up and ran down. And during the so when we are talking about the principles, we can just say, okay, this can be rectangular, and this is rectangular, and area between this is the same with this one. But for the practically, we actually need to apply the trapezoid shape of the gradient, and then we calculate the whole areas, including these ran ups and ran downs. And when during the, for example, this is the crusher gradients. So we can see that these two, the crusher gradient is by itself is also a trapezoid, but we can see that we are merging them together so that it's a more compact design, and it can save more times here, and it can also reduce some of the eddy currents that generate by the switching off of this gradient, right? So we can see that the ran down and this ran up here of the two gradients, they are connected together. So to make it a more compact design here. Okay, so here's another example. We saw this fast spin echo before. So there is another practical errors in this diagram. So if anyone can see that. Any thoughts? And also all this sequence I'm showing here, they are from the books. So. You have a thought?
I think the 5 volts is falling exactly after the slice.
Which one? You mean this one?
Should be an overlap.
Yeah, I think it's okay. It's okay, yeah. Probably not that obvious. So let's say they are not overlapped. Okay, so we have this slide selection here, but we are all missing all those slide selections gradients for the refocusing process. Normally you do not do slide selection and then do the non-selection process. Okay, so of course, when designing the fast spin echo, usually we will also use the so-called CPMG or RF phase alternation schemes. So it's also not shown in here. So usually this would be the excitation pulse. For example, if we apply the excitation pulse along the x-axis, then we will need to apply the refocusing pulse along the y-axis to avoid a signal, an additional signal dispersion due to the imperfect pi pulse. Because usually the 90-degree pulse is actually can be quite accurate. It can just be 90 degree. But if you, for the pi pulse, due to the failure of the block equation, right? So if we just simply use a sync pulse and increase the B1 field, actually it will not reach an exact 180-degree pulse. So usually it can be a little bit off. So when it's not an exact 180-degree pulse, there will be some signal loss, during these different refocusings. So using the CPMG can reduce this kind of signal loss caused by the refocusing pulse. Yeah. Okay. Okay, so yeah, here's the SPSP pulse you asked about. And here is the diffusion weighted imaging with the single unipolar diffusion gradients. So usually we apply the very strong sets of gradients along any or all of those axes. So this would increase the weighting on the diffusion effects. So this is the diffusion weighted sequence. And here is the top, the double inversion recovery pulse sequence for the black blood imaging. So it will, remove the blood signal to give you a black blood image. And here is example of the so-called arterial spin labeling. It is a very complicated. It has a very complicated signal preparation. It will tag the blood first in the neck, wait a little bit until this tagged blood goes into the brain, and then acquire the signal here in the brain. And then if you're interested, ASL is a very interesting sequence that you can use to estimate perfusion of the blood into the capillary in the brain. So this is the basic idea of the ASL. So I'm just showing here for you to see.
ASL, we acquired two images, right? One baseline and then subtracted.
I'm sorry?
In ASL, we acquired two images, right?
Yes. Yeah. It will collect a tag image and a control image. So a tag image is without the blood signal, and a control image is with the blood signal. So you subtract them together, and then you will get an image with only the blood signal. And this one shows that how the same sequence with different parameters can give you different image contrast. So with a short TE and short TR and short TE, you get a T1 weighted images, and with long TR and long TE, you get a T2 weighted contrast. And with a long TR and short TE, you can get basically get a proton density image contrast. So okay, so the final part should be more fun. So we need to take a look at artifact. So for artifact, if you see this artifact, you basically know that the author is from the Europe. So they, spell artifact with E. Okay, so the definition of artifact, according to the Webster dictionary, first one is the symbol object that was made by people in the past. So if we go to a Google image and input artifact, if it will give you all these images. So obviously this is not what we are looking for here. And the second definition is then accidental effect that causes incorrect results. So it looks like something that we do in MRI. Okay, so this is a more relevant definition by in the field of imaging processing. So an image artifact is any feature which appears in an image which is not present in the original imaged object. So that means it can give you some additional or some missing information or some misleading information. So here, if we take a look at the index at the end of the green book, we can find that it has listed all this type of artifact in the index. So for this multiple artifacts, some of them we have already seen during our past sections. Some of them are shown in the book. I think most of them are shown in the book. But this I think would be only less than 1/3 of the artifacts that MRI people have totally encountered. So there are still many more kind of artifacts out there. So some of them, this is some of those that I can think of. So for example, the magic angle artifact, the signal would have different signal intensity if the object itself is lying at a certain angle relative to the external Binov field. And data clipping due to the data acquisition amplifier, T2 shine through effect, partial volume effect, inflow and outflow of the blood, and FOB wrapping, third arm artifact as we just seen before, and radio frequency interference. And also there are lots of carelessness artifacts that is caused by human errors and improper design of the sequence. So for those, so the source of artifacts in MRI that can have be due to a multiple from multiple causes. So I think one of the major source is the hardware and electronic components. So the whole MRI scanner is a system is a very complicated system. So any failure or any glitch in those hardwares, or even the wire or small electronic components, can give you significant artifacts in the images. So we will see some of those examples later. And also there is environmental effect. So it is very important that you have choose a proper site of for the MRI scan, for the MRI scanner. So if you choose to put your MRI scanner next to a major road with all those 18-wheel trucks going just outside of the door, at the gates, like 100 feet away, the big chunk of metal can actually affect the field inhomogeneity of the magnetic field, or affect the electromagnetic integrity of the system. So it can give you some kind of artifact that whenever a big truck is passing through. And also you may want to avoid putting the scanner next to like an elevator or a corridor where those janitors may sweep the floor with one of those major floor washing machines. And all those may also cause some artifact that you cannot explain, because when you're inside the scanner room, you have no idea what's going on outside, right? But so it's very important. This is very important for the sighting for the MRI scanner. And also there are physiological effects for any live person. There are inevitable heartbeats, respirations. Sometimes if we are dealing with children and fetus, there are some motions that you cannot account for, and also blood flow. So all those physiological effects can give you some kind of troubles for certain MR sequences. And if there may be some implants problems. If the subject has the brace, it will generate a very strong susceptibility distortions, which may even affect the scan, in the brain. And sometimes the hygiene problem can be a cause of the artifacts. Once we scan a person with the scans a person on his head, and we found that the image was so blurry. We have no idea how to explain it. And then we have another person goes in and scan it. Everything turns out fine. So, and later on, then one of clinicians he suggested that the subjects go to wash his head. So after using the shampoo and wash, also squeeze from the hair, and then we put him back to the scanner and do the scan again. Everything turns out fine. So that means that if you have a very greasy hair, you might just it's better for you to wash it before you go into the scanner to image the brain. So this kind of artifact, you cannot. It's very difficult for you to to find out the source. But once you find out, it's very interesting that you know them. And of course, the operational error, right? When you set set imaging parameters, to a totally different set, it may give you, different artifacts. And also protocol settings, sequence design, and also signal processing, how to process the signal from the case space. It may also give you kind of artifacts, especially when you're doing research. And of course, the major part, of course, is the mysterious sources that you see an artifact, you have difficulty to understand it, and there are still many artifacts that we cannot, fully understand its underlying mechanisms. So what should be our attitude towards the artifacts that we see in MRI images? So first, we first need to accept that. We need to accept the fact that the artifacts are inevitable. So you basically have to deal with it. So some of the artifact is being significant, you can just see it right away and you know there is an artifact. Where others may be subtle, you may not be able to see there is an artifact unless you have a gold standard to compare to, right? But most of the time those artifacts can be removed or reduced or identified. So it's not too much a big deal. So apart from viewing the images, artifact itself can actually be very useful. So when we see an artifact, we know that something is wrong. So the artifact itself can be used as the symptoms of a disease, so that we can use it to diagnose the underlying source or the underlying problems to see whether it is the problem from the hardware or the problem of in the imaging parameters. And sometimes an artifact can be used to form some certain type of a new contrast mechanism. For example, the diffusion-weighted imaging. So the diffusion itself is was actually treated like an artifact. People have been trying to reduce its effect because it decays the signal. So, but nowadays, we actually want to enhance this diffusion-weighted effect so that we can get the underlying informations for the water molecules micro movements, and also the Bow effect and phase contrast flow quantification. They were all used to be treated like an artifact until someone came up and claimed that they were actually useful and can give us some useful information. And sometimes an artifact may be bad for some sequences, but may be good for others. And they can be used for fun in some rare cases, just like gradients. So I try to find out some of those examples that people use artifact for fun, but I couldn't find it. I remember there was a competition, so that people can show some artwork that is made from the MRI sequence, the artifacts. Okay, so here are some artifacts that we may routinely see during the MRI scan. So this is called a spikes artifact. A spike artifact is usually caused by some spikes or in the electronic components or in the wires, so that there is a high signal, a sudden spike of high signal in the K space. So depending on where this spike is located in the K space, it will give you different stripes, like artifacts that has different spatial frequencies. This one is the central point artifact. So we can see a bright point or sometimes a dark point at the exact center of the image. So this is caused by the shift of the receivers, so that there is a DC component in the K space throughout the whole K space. So when there is a DC component in the K space, its Fourier transform is at the center of the image. So this is center point artifact. This is actually can be considered like a more subtle one, because if it is located in the brain, it can be misdiagnosed as a tumor or a calcification or some abnormalities. This is the data clipping. So the data clipping, when we collect the data from using the RF coil, and this signal would first go through an amplifier, right, to enhance the signal before it reaches the image processor. So this, if the signal is already very strong, then it might have exceed the output limit of the amplifier, so that part of the high signals is being saturated or cut off. So it will lead to the. So usually the higher signal is located at the center of the echo. So a clipping of the center of the echo is like reducing the baseline signal, and also leading to some energy leakage outside of the objects. So this is kind of those data clipping artifacts. And also this is one of the most widely seen artifact we call aliasing. So this is usually when you set a FOV to be smaller than the object, so that the part of the object now is wrapped around and reappear on the other side of the FOV. This is another artifact that we usually see in the face imaging, which we call the cups artifact. So this cups artifact is like a singular point in the face image, a singular point. So after the processing, this may appear like a microbleed or something. So it can lead to a misdiagnosis. So the cause of this artifact is the combination of the different signals from multiple coil elements, so without any adjustment. And here is the radio reconstruction artifact. So if we have a full acquisition of the radio signal that meets the So if we have undersampled radio acquisitions, this is usually what this kind of artifacts can be seen on the radio acquisition images. And also this is the motion artifact, another widely seen artifact. So is that you move during the acquisition of the different phase encoding lines, so that the phase of the phase encoding lines, they are inconsistent. So when there is an inconsistence of phase in the K-space, there will be ghosting artifacts, or what we call the motion artifacts in the images. And here are some of the another example of the random RF interface. This was the data we collected a while ago. We are seeing these EPI images that have random signal variations. So we suspected, we are not very exactly sure what caused this, but we suspect it is because of the radio frequency interference coming outside the scanner room. So whenever the door of another MRI scanner room is opened, its RF frequency is leaking into the corridor into our scanner room. So this is that may be the cause of it, but we are not quite sure. But as long as the door of the other MRI scanner room is shut, we hardly see this kind of artifacts. Okay, so here are some. Let me see. Okay, here are some more subtle artifacts. So here is the T2 shrine full effect in diffusion weighted imaging. So for the T2, right, we have, if you remember the diffusion weighted image, let me go back, take a quick look at it. Okay, so this is the diffusion weighted image. So basically, the sequence. So basically, it is a spin echo sequence. So it will have a T2 weighting effect. So this means that this T2 weighting effect will lead to a high signal in the final diffusion coefficient maps, the calculated diffusion coefficient maps. So which is not due to the diffusion effect, but just due to the T2 weighting effect. So but in final map, the T2 effect may look exactly the same as the diffusion effect. And here is the arterial network collected using the contrast enhanced MRA. But because the contrast agent also enhances the veins at the same time, so we are showing a lot of vessels here, and sometimes we cannot tell which ones are arteries, which ones are veins. And here is the parallel imaging. If you have the new edition, the second edition of the new book, the parallel imaging is the last chapter. So for the parallel imaging, it will have this G factor map. So for the G factor map, the G factor effect will increase the noise in the image with the same pattern. So this kind of is like a localized noise enhancement. And this is the chemical shift. We have this shift of fast signal. Part of it is overlap with the tissue, and part of it is being pulled away from the tissue. So we are seeing there is enhancement, and there is a signal void in the I think this is the kidney, right? In the kidney. And here is data I collected a couple months ago. In here, we are using fast saturation to collect the image of the eye. So if we only look at this one, we do not quite see what there's anything wrong with this image. But if we use another new technique to suppress the fat only, we can see that there are actually many vessels inside the eyes, behind the eyes. So that means that the fat saturation pulse we use here actually have a very strong power leakage into the water signal, so that it basically also saturates the water signals in here, so that we do not see any of those vessels. And here are some of the artifacts that I collected for the past few years. So here is one of the sequences that I designed. So it's basically like EPI sequence, but with navigator. So we can see that for this one, first I put in the phantom. The phantom is just like this bottle. It contains water. So when I first put it in, the water is still flowing inside the phantom. So when I do the collection, we can see those signal variations due to the unsettled liquid. So this is the kind of like a motion artifact. And when it is totally settled, and this is the one of the best image I collect, we're still seeing that we should expect to see a homogeneous signal inside the whole phantom, because it's just the same water. But instead we are seeing that there's a kind of a signal reduction in the center, and there is a ring of high signal here. So this is caused by the dielectric effect of the B1 field. And here is the eddy current caused by the navigator once I have turned on the navigator. So this is the eddy current have led to phase discontinuity between the odd and even lines. So we are seeing this very strange. We are seeing this N/2 ghosting artifact. And also this is the image that I collected just before the liquid is settled down, and with the eddy current effect, we are seeing the signal is being totally ruined. Right. Okay, so here is another artifact. It's called a zipper artifact. The zipper artifact is it looks like a series of zipper dots, but it only takes place along one, zipper lines in random parts of the brain. So this is caused by the RF pulse interference. And this is the double echo sequence that I developed a while ago. So this was this artifact happened during the developmental stage. So it is basically a gradient echo, and then it collects two gradient echo sequence that collects two echoes, right? So the first echo looks great. It is well reconstructed, but for the second echo, all those signals they are just destroyed and dispersed. So basically, there's no usable information. So this is caused by the unbalanced gradients that I used before the second echo. So when I saw this image and I know my sequence, and I basically can immediately tell the problem, and then we solve the problem by adjusting the gradients accordingly. And for this one, we can see that there is some ragged edges of the phantom. So this was another sequence that I made. I tested. So this is caused by the signal pathway interference in the turbo spin echo. So if you remember the signal pathway concept we discussed in chapter 19, right? So this one is also susceptibility weighted imaging that we collected, gradient echo imaging we collected. So when we reformat it from the different view, then we can see that there may be some possible RF interference. So this image was collected roughly the same time as this one. So they may have the same source of the artifacts. And here is another temporary varying artifact that I came across when scanning the RF pulse, the EPI sequence. So we can see that when I'm collecting different time points, you can see this artifact here. It becomes stronger and stronger as time goes on. So this is caused by the gradient. Actually, it's the signal not being totally spoiled after the scan, after each TR. So, right. Okay, so for this section we don't have any specific homeworks, but if you are interested in the MRI artifacts, you can try to find a couple examples and try to solve find the cause and solve the solution to those artifacts. So for the next section, we'll do some reviews. The review will be focused on the SNR, resolution, imaging parameters, and image contrast. So mainly is the contents from chapter 15 to chapter 20. So it will be great that if you can come up with some specific questions in mind, and we can discuss it, on the blackboard. Okay. All right. Thank you.